Okay, thank you very much for joining. So today we are starting a new unit, which is our unit regarding computer system, networks and security. So this unit um, has three primary focuses. So we can see that firstly, we're now going to express our technologies that enable computers such as memory, programs, and the logic. So we will now look into our hardware side of things. And then we're also going to examine the software side of it, the connectivity and networking principles. So we all know that this approach is for underpinning knowledge for any IT practitioner, professional who should have a basic understanding of computer security. So this is level 4 qualification, and each assignment will now be graded with a pass, merit, and distinction. So this unit, we have three sessions. We will have 3 sessions on our assignment discussion. So in today's session, we're now going to understand enabling principles. So let's now get into our presentation. So what do we mean by enabling principles? We need to understand the technologies that we use in computing. So it is important for us to look at the fundamental technologies that form the basis of our modern computing system. So what are these fundamental technologies? We're going to look into memory, where we have a primary memory and a secondary memory and a cache memory. So the primary memory, which is a random access memory, we all know is a volatile type of memory because once this is now accessed by our computer and we switch off our computer, all the data will now be reset. While with our secondary memory, which is our ROM, this is not volatile, so any information that we stored stays in the computer. So for instance, images, videos, or whatever. While with our random access memory, we just need memory to access certain type of software and applications. Cache memory is a smaller, faster type of volatile memory, and it also provides high speed data access to our processor. Also, we have programs and softwares, which are, we all know that these are a set of instructions that have been given by our computer through our compiler. Low-level program and high-level programming languages, we have already explained them in our computer programming unit. So low-level language, such as assembly language, these are very much close to machine language and provides more control over the hardware. While high-level programming language, where we have to code with Python, Java, C++, C#, and so on, these are more abstract and they are user-friendly. Also, we have to look into the logic, where we're going to refer to logical operations such as Boolean algebra to now perform computations. So our logical operators are going to be our logic gates, which allows us to now build blocks, and we'll now be using and or operators. Then we have combinational logic, where circuits where output is the pure function and present input only. Then we have sequential logic, where we now know that the output is going to depend on the sequence of past inputs. So we're now looking to explain the difference between our hardware and our software. So with our hardware, we know that these are all the physical components which we can touch and we can now replace in case they're faulty. While software is, we're now looking more at the non-tangible aspect of our computer. So we're now looking into the program that we're now going to load into our machine to perform certain tasks. Then also it is important to look into connectivity and networking principles. So when it comes to network security, we now have to learn about the OSI models, which is the TCP IP model, and it is presented with different stages, different layers, and each layer is important for us to standardize communication function of our telecommunication. Networking components on the other side, we're now looking at physical devices such as our router, switches, modems, and also our network interface card. So we also have risks to computer system and data. So we need to understand what would be the risks that comes with our network. So the risks, there are various types of cyber attacks which could make our computer vulnerable. So here we have a couple examples of them, such as malware, phishing emails, denial of service, attack, and let's look at some of them. So malware, we know that these are malicious softwares, which will now gain access to our device, and they can now compromise our data. So they will now have data breach due to this malware that can now compromise the functionality of our computer, which we might slow it down or even eventually end the life of our device. Phishing, which are used to trick individuals into revealing sensitive data. And denial of service attack, this is where the machine, where they're going to attempt to make machine or our network resource unavailable to its intended users. So what could be our security tools to keep ourselves protected from any sort of attack? These are now antivirus softwares, firewalls, and encryption techniques. So there are many companies that provide antivirus software, which can be purchased for like a daily plan, for example. This will now allow us to protect our programs from any sort of attack and eliminate malwares. Firewalls, where we have security systems that are going to monitor and control any sort of incoming and outgoing network traffic. Encryption, where we're now going to convert our data in a way with a code which cannot be decrypted unless we have a key. Also, incidents and vulnerabilities. So what happens when there's a data breach? Basically, with the data breach, we now knowing that we know that we're going to have some data loss. So regarding if we are a small, medium, or large business, corporate, we will now have a data breach where our information is now leaked to unauthorized users. And this is this could turn into a massive problem for our company. And also we have a zero-day vulnerabilities where now with flaws software that are known to be to the vendor, and they can now be exploited by attackers before they are patched. So now we're going to describe the common unit and metrics in computing. So what do we mean by metrics? When it comes to looking into data, we all know that computers understand binary numbers, which is a sequence of input from 0 to 1. And these are essential for our computer operation and data representation. So binary, which is the smallest unit available for us, starts with the base of 2. Going on, we have octal, which is based on 8. Hexadecimal is based on 16, where we just keep on going up with the unit. And then we have base 64, where the use of 64 characters is used to encoding binary data in text formats such as email attachments. After number base, we have IEC binary prefix, such as kilobytes, megabyte, and gigabytes, and terabyte. So these we now looking at 2 to the power of 10 for kilobyte, 2 to the power of 20 for megabyte, 2 to the power of 30 for gigabyte, and 2 to the power of 40 for terabyte. So these are simply our capacity size. And also we need to look into speed. So this, when it comes to computational speed, we're also going to look into megabytes per second, or maybe megahertz per second. Okay, so we explained them. We looked into binary number with the base of 2, binary number with the base of 8, and hexadecimal, which is based of 16. Again, we covered what our binary prefix are. Okay, now we're going to look into explaining the role of different type of memory. So the role of different type of memory, it is very important component of our computer system, which we now have to look into classify them, such as volatile or non-volatile types. So we know random access memory is a volatile type of memory. Read-only memory is non-volatile. EPROM, erasable program ROM, this again is non-volatile. Electrically erasable program ROM falls under the category of non-volatile. NAND flash memory is non-volatile. Cache memory, this is non-volatile. Dynamic RAM falls in the volatile category, and a static RAM is again volatile. So let's look at the difference between the two of them. So with a volatile memory, this will now require power supplied into our machine to store, to maintain the stored information, while non-volatile will now retain our stored information even when the power is now turned off. So again, we looked into the types of them. We'll explain them. Now we're looking into data representation. When it comes to data representation computing, we need to know that this is a very important aspect because it now enables the encoding, storage, and manipulation of data in the form where our computer can now process them. So, data representation, now looking into data versus information, character set, parity, and checksum, where we have a description, and then on the right hand side we have the examples for them. So with data versus information, we know that we have raw data, unprocessed fact and figures. With character set, we have encoding schemes for representing text in computers, such as hash numbers and UTF. Parity, where we have error detection method that add an extra bit of data to make our number of ones even or odd. And checksum allows us to have a value calculated from a data set to verify its integrity. Cover them. So now we're going to explain storage program and languages. So we all know that these programs are now involved in exploring the architecture of our CPU, where we're now going to fetch execute cycle. So in our central process unit, as our CPU, we're now going to have a architecture. Then we're now going to have fetch execute cycle, low-level language, and high-level language, machine code, assembly language, programming languages, translator, virtual machine, and bytecode. So when it comes to programming language, we've already explained in our previous unit where we have high-level languages, which they might work with a compiler or an interpreter. And these programs are well known and used by developers, such as for interpreter programming language, we have JavaScript, Python, and for compiler programs, we now have C#, Java, C++, and so on. So let's look at our CPU architecture, where we're looking at the architecture. We're now going to use a single storage structure to hold both instruction and data. Then we have the Harvard architecture, where it's going to separate storage and signal pathways for instructions and data. Then we have fetch execute cycle. This is a fundamental operation cycle on our central process unit. And what this does is going to fetch in the CPU the instruction for memory. Then it's going to decode the instructions to determine if there is any action required. Then we're going to execute a certain program with certain instructions. And lastly, we're going to now store the results of our execution. Low-level languages, where we're now looking to assembly languages and machine code. These are the most basic program language, and they're entirely made with binary and hexadecimal instruction. Assembly language, these are now a step above machine code, and they're going to use a mnemonic code and labels to represent machine level instruction. And we already made an example for high level languages where these have the ability to understand human language, such as English, where we can now give a command, an input, and our machine is going to return an output for us. Translators, such as compilers, as I explained, is going to convert our high-level source code into machine code, and the entire program is now translated before the execution. Interpreters, this goes from high-level language such as Python and JavaScript, where the programming language is trying to interpret the command that you give into them. Virtual machine and bytecode. So virtual machine, we know that these are software simulation of a physical computer that can run programs in an isolated environment. Bytecode, on the other side, is an intermediate representation of the code that is executed by the virtual machine rather than directed by our hardware. Now we're going to look into our logical operators, which we spoke earlier. So basic logic in computing, we're now going to be understanding the basic logic, which are fundamental for computer science and programming. So here we have a table which summarizes our basic logic, such as the Boolean algebra. But these are basically a branch of algebra that is going to deal with true and false statements, such as and or. Then we have logical gate, which we're now going to have digital circuit stamps, digital circuits that perform logical operation on one or more binary input to produce a single binary output. Then we have Boolean algebra, where this is a mathematical structure that deals with binary variables and logical operations. Here we have more example of logical operation or where the condition has to be going to return true if at least one of our operations is true. Not with a negation, when a logical operation that returns true if operands are false, and false is the operand is true. And the basic negation. Inclusive or, with this, a logical operation. This is a logical operation that returns true if exactly one of the operands is true. While with logic gates, these are physical devices that are going to implement our Boolean functions, perform logical operation on one or more logical inputs. And here we have an example for them. You can see how and gate. So these are circuits which are very, we're going to find this if we study electrical engineering. So if we now have to code in PLC or like a Siemens PLC, we are now required to understand logical gate to understand how an electric circuit is now built. So here we have various examples of them. Also here we can have a practical application in programming. So conditional statement such as Boolean logic is fundamental in coding statements like if and else to control a program flow. And we have digital circuit simulations as well. So to conclude, we can see that basic logic encompassing Boolean algebra and logical gate is integral to both digital circuit design and computer programming. So Boolean algebra will now provide the theoretical foundation for making decisions based on logical conditions, while logic gates have now implemented this operation in the hardware side of it. So it is it's very important to understand these principles, which are required for any IT professional to design efficient algorithms and understand the inner working of our computer. So this was everything for today's session. Do you have any questions?
Thanks, Vic. That's really interesting. Yeah, well, I do have some questions. Basically, it's I could probably wait till Wednesday. So, ahead of like obviously starting the sessions this week, last week, because obviously they were supposed to start last week, but they got moved around. So I went ahead and had a little look at the assignment before this to just get an idea of sort of what we're going to be looking at and what we're going to be starting. I did have some questions around evidencing sort of like knowledge around like the first set of learning outcomes. So for learning outcomes 1, as I said, we'll be going over the assignment on Wednesday. So I'm not sure if that's really a question that should wait till then, or not.
It's up to you.
Well, might as well ask it now since we're here. So basically, I was looking at the assignment, and I think the first task is obviously looking at learning outcome 1, the different, the 5 different parts that make up learning outcome 1, and it's about creating a multi-question questionnaire, no, multi-response questionnaire, multiple answer questionnaire, for new people starting in the organization, in that scenario, coming in to sort of like test them in interviews, to do like a multi-answer questionnaire to see if their understanding of those areas.
Yeah.
And I just thought it was an interesting way of showing that you understand the criteria, because it's basically like learning outcome 1 is basically there's one describe question and 4 explain questions. So I've got a, for example, describe common units and metrics, explain the roles of different types of memories and that sort of thing. And it's like how to explain that, but present it in a question, a multi-answer question format. So I guess what I was thinking was like I could, I don't know, for example, when I'm talking about like the different types of memory, I could be talking about, megabytes, gigabytes, etc. Give an explanation of what they are, but then somehow embed that into the question, like, oh,
Yeah,
a gigabyte is such and such and such, or
yeah, that'll
is
be
it
easier.
such and such and such, or is it such and such? And then obviously in my answer sheet, I can then flag which one is the correct description. Just like, how do I explain things, but also put them in that question format? And I guess that's how I've kind of worked out in my head.
Yeah,
Um,
that would be the easiest way, I think, by giving
yeah,
the answer already in the question, maybe.
yeah, that's what I was thinking. So yeah, it'd be
Yeah,
it's definitely a different way of showing knowledge. But yeah, I like the challenge. So yeah, I just wanted to make sure that I sort of understood it
yeah, that's the way you have to go
correctly and then
with this
get
task.
confused.
No, it's fine.
All right, brilliant. All right, great. Well, yeah, that's sort of my one question for today, Victor. I'm going to go away and have a little more of a sort of dig around and sort of study into gates and stuff. And if I have any more questions around that, I'll maybe ask it in tomorrow's sessions if that's okay.
Okay, yeah, that would be great.
All right, brilliant. Great. Well, cheers for that, Victor. See you same time tomorrow.
Okay, see you tomorrow. Have a good
Uh,
day.
you too. Take care. Bye bye.